So let's continue. The next lecture is devoted to interaction of ionizing radiation with biological tissues, fundamentals of dosimetry. When we speak about radioactivity and ionizing radiation, we should begin from the structure or from the internal structure of atomic nuclei. So atomic nuclei consist of protons with charge 1.6 10 to minus 19 degree coulomb, mass 1.007 atomic mass unit, and the definition of atomic mass unit you can see in the slide, and neutrons with zero charge and with almost the same mass as protons. Usually we denote nuclei of atoms as follows. So here we have our chemical element from the Mendeleev element periodic table. Here we have mass number, A, number of nucleons in the nucleus to both protons and neutrons. And here we have number of protons in the nucleus or atomic number of element in the Mendeleev table, which is part of mass number A. For the estimation of radius of nucleus, we have empirical dependence, which you can see in this slide. These dependence show us how radius depends on mass number, as degree 1/3 of atomic mass number. Then isotope, we call the atoms of the chemical element which nuclei contain the same number of protons but different number of neutrons. And as an example of isotopes, we can consider such series of isotopes for carbon, including carbon-12, carbon-11, carbon-13, and carbon-14. When we consider the mass of nucleus, we should remember that it is not equal to the sum of masses of protons and neutrons. And in fact, if we take the total mass of nucleons and find the difference of this total mass and mass of nucleus, we obtain some certain non-zero value, delta M, which we called mass defect. This mass defect is related to the binding energy, which we find according to this formula. This energy required to bind the protons and neutrons in the nucleus. Radioactivity is a process as a result of which the nuclei of chemical element are spontaneously transformed into nuclei of another element. So we have two types of radioactivity, natural and artificial ones. Natural radioactivity occurs spontaneously without any external influence. It is the result of the instability of some nuclei. Artificial radioactivity is the decay of artificially obtained isotopes as a result of nuclear reaction. And nuclear reaction represents the transformation of some nuclei into others due to collision of nuclei with nuclei or particles with the nucleus. All radioactive decays can be grouped into radioactive transformation series or families. So we have such families: thorium, uranium, neptunium, and actinium. In 1990, Rutherford observed the disintegration of nitrogen bombarded by the nucleus of helium and obtain the oxygen-17 and proton, the nucleus of the hydrogen. It is first observed nuclear transformation. Then, according to the law of conservation of electric charge, we have the charge of the original atomic nucleus, sometimes called the parent nucleus, must be equal to the total charge of particles formed during radioactive decay and new nucleus, daughter nucleus. What main type of radioactivity we have? The first one, alpha decay of nuclei, is accompanied by the formation of alpha particles, nuclei of the helium atom, helium-4, which consists of 2 protons and 2 neutrons. And here you can see this chemical schematic reaction for alpha decay. And example, the transformation of radium 226 to ruthenium 222. As a result of alpha decay, the formation of daughter atom in the excited state and the formation of gamma radiation is possible, and radiation has a linear spectrum. Uranium, thorium, and radon are several natural isotopes that are a source of alpha particle. Then, the next one, beta decay, the transformation of protons and neutrons inside the nucleus. Electron or beta minus decay when fast electrons fly out of the nucleus of the atom with formation of antineutrino. So we have such schematical reaction. And example is the decay of carbon 14 with formation of nitrogen 14 electron and antineutrino. As a result of beta decay, continuous spectrum is formed. Positron or beta plus decay, we have such schematic reaction when we have formation of nucleus with charge that -1 with formation of positron and neutrino. So the example is the decay of carbon 11 with formation of boron 11, positron and neutrino. K capture or capture of electron from the inner orbit of the atom, causing the protons to turn into neutrons. So what we have? Here is our atomic nucleus. Here we have nearest orbit to this nucleus. So we have electron capture by our nucleus with schematical reaction. While he captured the formation of characteristic X-rays occurs. So what we have, for example, for beryllium, we have a capture of electron from the inner orbit with formation of lithium-7 and X-ray characteristic radiation. Gamma radiation represents the short-wave electromagnetic radiation with wavelengths less than 10 to -10 meters. The gamma quantum of energy rises during the transition of nucleus from the excited states, for example, with energy E2 to excited states with energy E1. Energy of gamma photon and gamma radiation can be found according to Bohr-Sommerfeld formula, where its frequency is proportional to the difference of energy between these levels. And example can be transformation of excited uranium 239 to less excited uranium 239. Then, what we know about neutrons? Neutrons are naturally present in space, but are also formed as a result of fusion processes that makes place in nuclear reactors. Neutron radiation can travel long distances in the air, making it source of the main dose for population living near the nuclear power plant. Neutron protection is complex and not always successful. This will require many layers of different materials, and the most effective means of protection against neutrons are water or hydrocarbons, such as hot paraffins and concrete. Unlike the radioactive radiation, other radioactive radiation, neutron radiation can turn more substances into radioactive ones to different degrees, including air, water, soil, and body tissues. In this table, you can see physical properties of ionizing radiation. So the type radiation, alpha, beta, gamma, neutrons, the characteristic energy in mega electron volts, and corresponding values. Then free pass length in the air up to full stop. So you can see that free pass length is the greatest for neutrons. Free pass length in tissues, this column, and ionizing force or number of ion pairs per 1 centimeter free path length. So you can see that the greatest ionizing force we have for alpha particles and for neutrons. Then the rate of spontaneous decay, the number of nuclei that decay at a given time, varies according to such law. When we integrate this differential equation, we obtain exponential law of radioactive decay, whereas lambda is radioactive decay constant. The same part of available radioactive nuclei decays per unit time, N represents the number of nuclei at a given time, and N0 is number of nuclei at initial time, T equal to 0. So here is our initial number of nuclei, and then we have exponential decrease with time. Half-life period is time during which half of the nuclei or the radioactive samples decays. So we find the 1/2 of initial number, and here is our half-life period, which we can find as follows: logarithm 2 divided by radioactive decay constant. The rate of radioactive decay, that is number of decays per unit time, we called activity, so we can write such expression. The unit of measurement of activity is becquerel, which represents 1 decay per 1 second, but as we have too many decays in second, it is more convenient to use non-systematic units of measurement, Curie, which give us 3.710 to the 10th degree becquerel. The activity of the radioactive isotope or radionuclide is greater the number of radioactive nuclei and at a given time, and the shorter the half-life period. As for effect of radioactive radiation on matter, what we can observe. The first one is elastic scattering, a change of radiation direction. Then we have violation of atoms and molecules, which leads to a chemical reaction and formation of highly active compounds. A photo effect, separation of electron from an atom. This leads to ionization. Nuclear reaction, which leads to changes in conductivity, formation of nuclear fragment, daughter nuclei, heat dissipation, luminescent ability, and grid penetration power. The effect of radiation on the human body. At the molecular level, the violation of the structure of molecules. At the cellular level, the violation of the apparatus of cell division and the function of differentiation. At the tissue level, affected tissue in which cells are rapidly renewed, such as bone marrow, blood cells do not mature, integumentary epithelium in the lungs, intestines. Protection against ionizing radiation includes 3 types. of protection. Protection by time, distance, and material. Material protection is based on the different ability of substances to absorb different types of ionizing radiation. For example, when the dentist works on the X-ray machine, radiation from the X-ray tubes and scattered radiation from the patient are possible. Absorbed materials, for example, lead, are used to protect the doctor and the patient. The main problem with the safety of X-ray machines is secondary scattered radiation, and about 20 or 30% of secondary radiation emanating from the patient falls on the operator holding the X-ray tube. Here in this picture, you can see the protection from the different kind of radiation, including alpha radiation. Alpha particle can be retained even by sheet of paper. Beta radiation can penetrate through paper, but can be stopped by lead and concrete. And for gamma radiation, we can stop it only for very thick layer of concrete, hydrocarbons, and water containers. Research of background radiation, natural and artificial. What we have? As a result, we have risks of children's oncological diseases. In all cases, increase owing to irradiation, which is a little exceeding natural annual doses. Among children's oncological diseases, leukemias and oncological diseases of the central nervous system prevail. Radioactive contamination is likely to have a strong impact on the individual adaptability of present and future generation, with potentially significant consequences at the population level, even outside areas contaminated with radioactive materials. Radioactivity is also associated with negative latent health effects such as nervous system disorders and low coefficient of intelligence. Radiation can increase the resistance of bacteria to antibiotics. And it seems that radiation can affect estrogen production, which indicates that in addition to cancerogenic effect, radioactivity can lead to disorders of the endocrine system. Estrogen is key to a healthy pregnancy and adolescence, and is more abundant in a woman than in a man. As for characteristics of ionizing ability, we can describe it in terms of linear ionization density, I, whereas the N represents the number of ion pairs formed by the ionizing particles in the elementary path. And then mean linear range, the average distance traveled by the ionizing particle in the substance to a complete stop, and linear breaking ability, which is given by the rate of energy lost by particle during the passage of unit part in matter. As for elements of dosimetry of radioactive radiation, what we have? We can characterize it in terms. Absorbed dose, which represent the energy of radioactive radiation absorbed by mass of our substance. Units of measurement is gray in C and non-systematic red. Exposure dose give us the charge of ions of the same sign arising in the mass of substance as a result of radiation exposure. CI units, coulomb per kilogram, non-systematic or Röntgen, with such definition. One Röntgen represent 2.6 10 to minus 4 coulomb per kilogram. Biologically, all equivalent dose give us difference for possible damage from different type of radiation. So we take our absorbed dose with appropriate quality factor, which depends on the type of radiation. So for the gamma, beta radiation and X-rays, this factor is 1. For neutron flux, we have quality factor varying from 3 to 10, and for alpha radiation, it is about 20. Units of measurement in CI, Sievert, non-systematic, RAM, radioactive equivalent man, whereas for absorbed dose, red, we have radioactive absorbed dose abbreviation. From such consideration, we can conclude that not only the radiation dose is important, but also the time during which the object is exposed to radiation. For the human population, the lethal absorbed dose can be from 3 to 8 gray or 300-800 red when the general irradiation of the body with X-rays. And the absorbed dose, which is less than 1 gray or 100 red, the probability of death is very small, whereas if the absorbed dose greater than 8 gray or 800 red, the probability of survival is already very small. At absorbed doses, 10 gray, 1000 red, death occurs from the damage to white blood cells, mainly lymphocytes. At much higher absorbed doses of radiation at level of 100 grays, there is a catastrophic death of cells of the gastrointestinal tract, and at even higher doses, cells of the central nervous system die. The permissible biological dose, when irradiated, is 50 millisievert for 1 year. The lethal biological dose at irradiation is 6 sievert. Natural radioactive sources create the ground of 125 millirem. According to the result of analysis in 2019 in Ukraine, the effective dose limit for category A personnel is 20 millisievert per year. The average annual doses for different medical institutions varied between 0.4 to millisievert for the staff of radiological departments working with gamma radiation sources, 0.4, 8.9 millisievert for the staff of X-ray diagnostic departments. The generalized average annual radiation dose of medical staff of all medical institutions of Ukraine when working with gamma radiation sources was 0.58 millisievert. When working with X-ray sources, 0.54 millisievert. If we take into account the time of exposing, we come to dose of rate intensity, which defines as absorbed power. It gives us rate of change of our absorbed dose with time. Exposure power gives us a ratio of our exposure power to a period of time. Biological dose correspondingly give us the rate of change of our equivalent dose to period of time. So we have units of measurement: gray second to red second, Roentgens per second, and sievert per second, or RAM per second. Application of ionizing radiation sources in medical practice include diagnostic radiology and beam therapy. Diagnostic Radiology includes the röntgenoscopy, X-ray radiography, fluorography, computer tomography, radionuclide diagnostics with in vivo and in vitro studies. And as for therapy, we have beam therapy, which divides into three classes: external, contact, and internal. Radionuclide diagnostics represent methods of visualization of organs and systems by administering to the patient special diagnostic radiopharmaceutical preparates labeled with radionuclides. Radionuclide diagnosis is of two types: in vitro in test tube and in vivo in the body. A diagnosis of cancer in vitro is performed without the introduction of radionuclide drugs into the patient body. For diagnostic purposes, a biopsy of tissues of the lesion is performed. Tissue samples are placed in a test tube where the interaction with radioactive isotopes take place, and this is methods of radioimmune analysis. A radionuclide diagnostic in vivo is a method in which radionuclides are injected into the human body, and then their location, rate of accumulation, activity in organs and tissues are determined with gamma cameras, with SPECT and PET tomographs. For example, to diagnose thyroid diseases, we use radioactive iodine 135 or iodine 131 radionuclide, part of which is concentrated in iron. We inject it into the blood. The rate of increase in the concentration of iodine leads to conclusions about the state of thyroid gland. As non-functional thyroid tissue does not absorb such a substance, it forms a less radioactive region in thyroid gland, which is detected by surface radiation detectors, gamma tomograph, a device which records the intensity distribution of radioactive drag. Positron emission tomography represents the methods of studying the functional state of body tissues with the help of radionuclides emitting positrons, which are passing through human tissue 1 to 3 millimeters. After interaction of the positron with the electron, 2 photons of gamma radiation with energy, which we find as follows, are formed, and they fly in opposite direction. Isotopes with a short half-life are used. Carbon-11 with a half-life period of 20 minutes, nitrogen-13 with half-life period 10 minutes, and oxygen-15 with a half-life period of 2 minutes. Fluorum 18 with half-life period of 110 minutes. All of them are able to positron decay. The images show processes occurring at the molecular and cellular levels, including the glucose, carbohydrate, fat, and protein metabolism, blood flow and perfusion estimation, receptor concentration estimation, study of molecular transport process, membrane permeability and receptor state, study of drug distribution and their pharmacokinetics. These methods give us possibility for early diagnosis of various diseases before appearance of structural changes, monitoring of therapy with early estimation of the effectiveness of treatment, which enable to reduce the duration of treatment and in some cases to avoid hospitalization. Replacing a series of studies with one, the most informative, forecasting the result of surgical treatment and detection of distant metastases, which can radically affect the tactics of treatment. Therapeutic radiology. Malignant tumor cells divide more often than the normal tissue cells. Cancer cells and sarcoma cells are very sensitive to ionizing radiation. Normal tissues has a greater ability to recover from the effect of ionizing radiation than malignant tumor cells. Thus, the radiation dose is sufficient to kill cancer cells. The most often, radiation is used to treat cancer patients in conjunction with surgery and treatment with anti-cancer drugs. Radiation is used as a standalone method in the treatment of cancer. And here you can see this type, the skins of the lip, tonsils, pharynx, cervix, uteri, and so on, at initial stages of lymphoma and sarcoma. In the treatment of other cancers, radioactive therapy is used only as part of comprehensive course of therapy. And there are several types of medical exposure in radiation therapy, depending on which particles are irradiated tumor with. Corpuscular therapy, including alpha and beta particles, as well as beams of neutrons, electrons, and protons. Photon therapy is carried out due to the influence of gamma and X-rays. Brachytherapy or contact radiation therapy is type of radiotherapy when radiation sources radium-226, iridium-192, iodine-125, cesium-137, cobalt-60 is injected into the affected organ. The advantage of the methods is ability to bring the maximum dose of radiation therapy directly into tumor area, while minimizing the effect on other organs and adjacent tissues. It is widely used in the treatment of tumors of the cervix, uteri, body of the uterus, prostate, vagina, esophagus, rectum, and anus. The use of alpha particles in the therapy is associated with their significantly near ionization density. Substance introduced into tumor, the nuclei of which are direction of neutrons, cause a nuclear reaction with formation of alpha particle. Here you can see an example of such reaction. Alpha particles that are formed inside the body cause destructive action. Gamma radiation causes ionization of biotissues molecules at any distance from the body surface. This enables to destroy deep tumors, and the source of gamma radiation is cobalt-60. Gamma rays emitted by radioactive cobalt provide a high effective dose of radiation of tumors of deep tissues of the body. Protons give maximum of ionization at the end of their free path in the matter. To ensure the depth of penetration into tissue by 11 or 14 centimeters, proton beams must have an energy of 120-160 mega electron volts. Neutrons with an energy of 10 to 15 mega electron volts give the distribution of ionization by tissue depth similar to analogical effect in X-ray irradiation. And the maximum of ionizing effect is located on surface of the body area that is irradiated. To obtain the beam of charged high energy particles of certain energy, we use an accelerators. Accelerators can be linear and cyclic. For example, cyclotron and synchrotron for heavy particles, betatron for acceleration of low energy electrons. Charged particles accelerator can be used as means of radiation therapy in two main directions. First, we can use break-in auxiliary radiation, which occurs during the breaking of electrons accelerated by betatron. An electron with energy of several tens of mega electron volts leads to a break-in radiation, which is more efficient than the gamma radiation of most isotopes. Secondly, we can use the direct action of accelerated particles, electrons, protons. The protons accelerated in the betatron and proton beam obtained from the other electrons. When a beam of protons enters a biological object from the outside, the greatest impact will be given not to the surface layers, but to the tumor's tissue, which are located more deeply in the body. The small scattering of protons allows the formation of narrow beams and thus very accurately affect the tumor. Along with the therapeutic use of accelerators in recent years, we have the possibility of using them in diagnostics. So for today, it is all. Thank you for your attention and goodbye.